Hello everyone. Good evening to one and all, and happy Independence Day. Today we are here for the knowledge sharing session. A very small introduction about the speaker. Our speaker's name is Samarth Prabhu. He's doing his mechanical engineering fifth sem. You can see it on his screen also. So he's a former intern at JNCASR Bangalore, aspiring physicist. So he'll be sharing his thoughts on scientific thinking. This is presented to you by AAC's Physics SIG. So uh, here the speaker will be discussing the philosophy of science and mathematics and why is it important.
Okay, all right. Thank you, Srinidhi. So, today's topic is scientific thinking. I'm Samarth Prabhu, and I'm studying mechanical engineering, my fifth sem at NITK. These are my contact details. You can contact me here and here. So, okay then. So, is my cursor visible? Is my mouse visible? Yeah.
Yes.
Yes, yes, it is.
Okay. Okay. All right then. Let's move on. So, okay then. What is science? The etymology of science. Yeah. The word science comes from the word "scire" from Latin, which means know, which then further developed, as all languages do, into scientia, which means knowledge, and then further developed into the word we know today, science. So, what is science? So, it is a system that builds knowledge in the form of testable explanations about the universe. Let me reiterate that. It's a system that builds knowledge in the form of testable explanations about the universe. So, the earliest we know of science is about 3000 BCE, when in the Mesopotamian era and all that. Back then, there was no solid concept of rigor and testing in science. That's why we should consider those as proto-science. I've added three things from my screen: proto-science, pre-science, and pseudoscience in my in this slide. Let me explain what each of them means. Proto-science is science before the testing. So, take for example, uh, Einstein's general relativity. General relativity was logically derived from math and previous experiments, but it was still not verified, not until Arthur Eddington's experiment in the 1930s, and then subsequently the Pound-Ripka experiments, and then in 2017 the LIGO, what do you call, gravitational wave experiment, and all that. So after it was verified, we can fully classify general relativity to be science. Now returning back to proto-science, pre-science, and pseudoscience. Now proto-science is science before science. That's okay. Pre-science is science in the era where there was no concept of rigorous testing, the scientific method, nothing. This disciplines such as Ayurveda, traditional medicine, etc., fall under this category because they were uh, they were existent in an era where there was no knowledge of chemistry or biology or something else. Which and pseudoscience is just blatantly wrong. That's all. Facts which are presented as blatantly wrong are pseudoscience. For example, the 1998 vaccine fiasco. You know that criminal called Doctor in quotation marks Andrew Wakefield. He produced a paper in the New England Journal of Medicine, which linked vaccines to autism, which sparked a new generation of anti-vaxxers and all that, and also causing measles epidemics in Africa and the other countries due to his one wrong paper. That is why pseudoscience must never be taken very seriously and must always be disregarded. Now, Moving on. So I said pseudoscience must be disregarded. It requires a certain skill called as critical thinking. Critical thinking is one of the most important skills that one can have, and as a scientist, it is a fundamental skill to have. Now, it is broadly split into seven parts. Okay, the first one being analysis. You analyze the problem, and then you source the data, and then you apply the necessary mathematical methods and tools to to decipher what to simplify the data. Next comes interpretation. So we have to properly interpret the data because which requires some certain amount of background knowledge. Inference. Inference is when you infer data basically. So one can come to wrong conclusions, such as the vaccine study, even with all the right data if you want. Which is why we have to properly take a step back and look into what the inferences are. And then we have self-regulation. So it is a way of telling that we do not get ahead of ourselves and try to imply try to what you call promise the stars when you have only peanuts. Yeah. And now open-mindedness. This is a very important skill that many of us lack today. The moment our viewpoint is countered by a factual claim, most of us go become defensive. A scientist is supposed to consider every possibility of an argument, the truth, the falsity, and keep an open mind to more truths about the universe and problem solving. The more you solve problems, the better you understand them. Okay, then critical thinking in the philosophy of science. Sir Karl Popper's name is a very is at right at the top. So Karl Popper he uh, in- he introduced a topic called as falsifiability of testing. When we say we test something, uh, it is through a system of observations. Now, what does one mean by falsifiability? So the statement of observations that can be created in a logical structure must be independent from factual observations. So how you observe data must be independent from fact or reality. What does this mean? So to test whether the general relativity was true, we had to set Pound and Ripka had to set up an experiment, which I'm not going to delve too much into, and they had to set it up in such a way that it did not basically confirm the theories. It had to be either true or false, which means when it is tested, the experiment must produce either a true result or a false result. It can't simply act on a confirmation bias. Then people can sometimes naively, what do you call, classify falsification as every theory in science is false. We can say that, and it is certainly true. Thinking of falsifiability in this way, every theory in science is false, strictly speaking. But this way of thinking is practically useless because the theories we currently have are very nicely explain how our universe works. So, to quote Abhishek Upmanyu from his famous stand-up bits, universe इतना बड़ा है, संसार में हम कुछ नहीं. When his friend says, Abhishek replies with, तो फिर मैं क्या job छोड़ दूं? So uh, this sentiment is rather what do you call, which it holds us back. So that's about it. And this is one of the methods of critical thinking called the scientific method, which is basically what science is right now. So, who is a scientist? A person who applies the scientific method, and that's about it, naively speaking. So, first we ask a question, then we research on background, then we construct a hypothesis, then we test it with with a falsifiable experiment. If it is working, then analyze data and draw conclusions. Results, if they match with your hypothesis, spread it around in a paper, like publish your paper. If the experiment doesn't work, okay, analyze the data and draw conclusions. If the data doesn't amount to anything, is change your procedure, reconstruct your no, change your procedure and test again, and then analyze the data. If the results align with the hypothesis, uh, communicate with spread it around in a paper. If the results don't align, we go back to the construct hypothesis part, tweak the hypothesis, and then test again and again and again, and then we have the science of today. So that's enough about science now. So let's switch over to mathematics. So mathematics is a broad topic, so broad that there is no accepted definition for it. Uh, so one can say that it is a study of quantity, space, measurement, space, change, and the others, and the same pedantic textbook definitions. But my favorite definition of all, but although rather oversimplified, is mathematics is four kids called space, change, structure, and quantity sitting on top of each other with a trench coat called logic. So, hope you understand what I'm saying here. India has always been at the forefront of the early mathematics scene, with people like Bodhyana, Pingala, Brahmagupta, and the others giving us zero, negative numbers, trigonometry, and even rudimentary differential calculus. How does mathematics work? Mathematics works by using arguments which can be shown to be deduced from a set of basic statements called axioms. Okay, then we accept some statements to be obviously true, and they're called axioms, and then we use logic and deductive reasoning to get to validate or invalidate arguments. So an axiom can be literally anything. So if I state an axiom that the plus symbol means something else, that's it. We can just accept the hypothesis and move forward and create new mathematics. Say one, we can even prove 1 plus 1 is equal to 3 by redefining how plus works, how 1 works, how equal to works, and all that, and just redefine and change mathematics. But mathematicians have tried various axiomatic systems, and then just chose the most convenient of them all, which is called Zermelo-Fraenkel set theory with the axiom of change. From this set of axioms created by Giuseppe Peano, Zermelo, Ernst Zermelo, Fraenkel, and many others, we can deduce almost all of mathematics here. I talked about axioms giving us arguments which can be validated or invalidated. These arguments are called as proofs. So most proofs use formal logic and some normal language to validate or invalidate an argument. So using of normal language here allows for some ambiguity, but that's okay because this so that theorem is sufficiently communicable to the masses and the other academicians. So there are totally symbolic proofs involving nothing of human language. And there's a separate area of study called proof theory, which just studies how proofs work. And it's quite interesting to see how mathematics has risen to new levels of meta, where they just analyze how proof works, how reasoning works, and it's beautiful to look at. So there are talking of proofs. There's a few categories of proofs which I have listed here. One is called as the direct proof, prove that the sum of two integers is even. So we have 2m plus 2n, add them both, and we have 2 times m plus n. 2 times m plus n is even, thus sum of two integers, two even integers is even. Proof by contraposition. So if we have a statement P implies Q, we've studied back in our high school days that P implies Q is logically the same as not Q implies not P, which is the contrapositive of the statement. So to prove, I've just given a small example problem here. If x squared is even, then x is even. Prove this statement. So how do we go about it? Then we prove that if x is odd, then x squared is odd. That is, although there are direct proofs of the given statement, proving that x is odd implies x squared is odd is a cleaner method to go about it. All right, proof by contradiction. This is one of my favorite ones. So to disprove a theorem, disprove a conjecture, it is enough to show that there exists one contradictory element to it. So in 1966, people did what was thought literally impossible to disprove the king of mathematics, Leonard Euler himself, in the by disproving his sum of powers conjecture. Here it is. So the sum of power conjecture is Euler trying to generalize Fermat's last theorem, which states that uh, which states something. We all know what it is, and it's not necessary right now. So it tries to generalize the sum Fermat's last theorem. So can it be applied to more than two integers, resulting in another power? So they just did a direct search on CDC 6600, which is the which is a good supercomputer in 1966. They just came up with this counter example, which meant that Euler's sum of power conjecture was wrong. And I quite like this paper because it was the shortest maths paper published in a serious journal for its time. And John Conway has come up with shorter papers, but I quite like this paper because one doesn't simply come up with a contradictory proof for the king of mathematics. All right, then. So then we have proof by construction. So Joseph Lewin, famous number theorist in the 1800s to 1900s, he constructed a number which then he proved to be transcendental. What are transcendental numbers? Transcendental numbers are numbers which cannot be expressed algebraically. What does that mean? If we have a number x which is transcendental, we cannot find a polynomial equation which has a root at the number x. So some of the famous transcendental numbers are e, pi, and Lewell's constant, Chapernaun's constant, and the others, and so on and so forth. Then finally, we have proof by exhaustion. This is usually a computer-assisted proof. In graph theory, there's a famous theorem called four-color theorem, which states that every map can be colored in using only four colors. I apologize if there are any computer scientists or pure mathematicians in this talk, but roughly speaking, every map can be colored using a maximum of 4 colors. So what mathematicians did is they took all possible cases of maps, which were 1936 cases of maps, and then verified it using a computer, thus proving the four color theorem. The problem with a proof by exhaustion or a computer aided proof is that it doesn't allow us to delve further into mathematics. It doesn't imply anything. It's just that, and that's it. So we have this question: is physics axiomatizable? We'll get back to that. Get back to that later. So now I'll just give you just pause for a moment and take any questions. Anyone?
Can I ask a question?
Sure, go on.
Yeah. So it's not directly related to what you've been saying,
Okay.
but it's about employing the method of science to study nature.
Okay.
Uh, because it occurs to me that all the theories that we have in science, such as GR and QFT and other field theories or any other theory, they are a result of our thought process. I mean, by that I mean to say, you were mentioning about critical thinking, right?
Yeah.
Yeah. So in this regard, I would like to look at thinking as a measurement. Uh, by that I mean, thinking itself is a physical process that's measuring events in nature. And out of the series of measurements thinking makes, they are assembled as facts and a theory is built, right?
Uh, yeah, that's practically how the scientific method works. We
Yeah,
think,
yeah. So I was,
we see, we think, we analyze, we test,
yeah,
we publish.
yeah, certainly, certainly. And I was wondering if to really understand nature, like in the sense, if one wants to say, akin to the unified field theories that we have, if one were to describe the most fundamental aspects of nature, should it not cover the origin of thinking as well?
Origin of thinking, you mean?
Yeah, like,
I
yeah, what's the source of thought? Because thinking itself is a part of nature, it's a natural process.
okay, the
And to
self-reference.
study, like, because to me, actually, I was working on similar ideas in my UG in NITK, like energy and general relativity and things like that. And then it occurred to me this question that I asked, that all these theories that we do are a result of thought process. So is there a way to find out how to think? Like how does one approach the source of thought?
How does one naively? I don't understand the physical concepts of it. I mean the philosophical concepts of it. But
Mhm.
naively, I can say that thinking is a process of the brain, and biologists have been doing work. Whoever's been studying brains has been doing work on
Yeah, yeah,
thinking. That's naively. But
yeah.
then
So I am.
philosophically, I don't know actually.
So I'm
Science
this.
is
Yeah, I do this science actually. This is the kind of work I do. Right now, I'm doing theoretical physics for biological systems, but and I see the same problem here as well. Uh, the what you just mentioned as people studying the brain, trying to come up with ideas to model thinking, etc.
yeah, yeah.
That doesn't seem to be working actually. So I was just putting forth, but yeah, it's like I said, it's not directly related to what you had been saying, so it can be avoided. It can
So
be
yeah.
looked into.
Yeah, because science is not physics, chemistry, maths, biology, and I mean not maths, physics, chemistry, biology, and all the Venn diagrams in between. Science is just one.
Right,
Physics, chemistry,
right,
biology are just artificial boundaries that we have for our own convenience.
right.
So maybe there are aspects which are present in physics which we need here. We need to model electrons on how currents work
Mm,
in the brain and all that. Maybe
right,
we
right.
just haven't come up with enough theory on how consciousness works. The
I
fact
see,
that
I see.
we've come to this part is
Right,
great because we knew absolutely nothing back say 100, 200 years ago.
Right,
So
certainly, certainly.
depending on how much time has passed, maybe we can model how thinking works.
I see, certainly. Okay, thanks.
So this is physics axiomatizable? This is a very profound question asked by this bearded guy in a cool hat. His name is David Hilbert or Hilbert. I don't know how one pronounces it. So this is the greatest mathematician in the 20th century by far. So he proposed 23 problems which he deemed as the most fundamental problems to mathematics. Just read upon Hilbert's 23 problems and you'll know. The 10th problem is the Riemann hypothesis. I don't know. What do you think? Is it open? So never mind. Uh, so the sixth problem, which is open till date, asks if the laws of physics can be logically derived from basic statements. Okay, what does that mean? So can we have all of physics be derived from basic statements such as F is equal to ma, or maybe the Euler-Lagrange equations? Probably this is what he asked. This is a rather philosophical and vaguely posed problem, which is why it is still open today. So now, I personally, I don't think physical problems can be axiomatized that simply, because physics isn't totally logically derived. It has a need for empirical evidence, which means we have to look at the universe, we have to observe the universe to be to be understanding the truth. To understand the truth, we need to observe, which means that the axioms must include some physics. Say the shape of the universe. Is it concave? Is it convex? Is it hyperbolic? Is it a Poincare sphere? We don't know. We can't see. We can't test it. That's why it's a little open. I don't know. This problem requires its own importance. Physicists have been thinking about it for a long time. Hilbert himself was excited to maybe axiomatize, but then maybe disappointed because he couldn't. Now let's move over to logical fallacies. In critical thinking, sometimes we've talked. Sometimes your reasoning can be faulty, which leads to invalid arguments. This this error in reasoning is called as logical fallacies, and there are quite a few of them, and some of them hit too close to home. So logical fallacies. So if we take random axioms and derive faulty conclusions from that, uh, uh, it can't be. It is valid, but it is fallacious because it isn't close to the truth. So what is science? Science is basically coming close to the natural truth as much as possible. So usually in debates we have the most common logical fallacies, such as the ad hominem fallacy. When your opponent has presented you with a fact, you start attacking the opponent by calling him a moron instead of considering his tackling his argument. We've all seen this happen all around us in the media and etc. Okay, and one should always keep in mind that it does not matter who the who the opponent is. What only matters is his argument. Is it true? Then discuss why it is. If it's false, discuss why it isn't. The person speaking does not matter here. All right, then. The second most common, which I've noticed, is the strawman fallacy. Strawman is when you pick a part of the opponent's argument and then start criticizing on it. So, say for example, if you say that we need to increase our budget about on healthcare and education, so someone else says that you are unpatriotic because they only see you're unpatriotic. Why should we decrease military spending? So what the problem in this statement is the opponent just took the point of healthcare expenditure being increased and extended it to mean that military funding should be decreased. Again, this isn't a very good strategy, because most people can identify and are annoyed with the strawman policy. The next one is my favorite by far. It's called the tu quoque argument. It's or the appeal to hypocrisy. So let me give an example of what the tu quoque argument is. So when a smoker says that smoking is injurious to health, or a random person comes and says, but you are a smoker yourself, how can you say that smoking is injurious to health? Which means your argument must be wrong. We've seen this plenty of times. I've been victim to this so many times back in school and college, everywhere. It's like it's the moral character of a this is of a debater is irrelevant to the argument about argument to the argument. So when a murderer says that murder is wrong, and people start bashing him because he himself is a murderer, how can he say that murdering is wrong? Does not change the fact that murder is wrong. So people, this is a very common policy to fall victim to. So now that you guys know, have been know now that you guys know, just please do be careful about using two co-quay arguments. And then next one is burden of proof. This one is rather annoying, because this is used by flat earthers and anti-vaxxers to try to credit their fringe science and discredit modern medicine. So they just argue that it must be true because it hasn't been proven false. So the reality is not that way. So we don't know if it is true or false. So you can't assume one or the other. Basically, extraordinary claims require extraordinary proof. So if you're claiming that the sun is a sun is a bag of ice cream, you'll have to back your statement up with necessary and substantial proof, especially for a claim as tall as the sun is a bag of ice cream. Okay, then I'll move on to the middle ground fallacy. This one is a this one is a corollary of the burden of proof fallacy. Sometimes people middle ground fallacy is that either one of the two positions, the truth or falsity, must be can't be proven right, is fallacious. That's why the middle ground is false. Let me give you an example instead of using all these complicated definitions. So when we say vaccines work, and then vaccines work and don't cause autism, and then an autism fringe group comes and says that vaccines do cause autism, one cannot logically say that some vaccines cause autism as a way of inducing truce in between between the two opposing parties. So we all know that vaccines are very effective, and they have been tested to a very high degree, and have been very safe for a long time. That's why uh, that's why we know that the middle ground is fallacious. The middle ground policy in itself is sometimes very hard to identify, because it is very appealing, because humans do not like conflict. We absolutely try to avoid conflict in all areas, but a scientist, or at least a true man of science, always stands by his beliefs, and always provides necessary proof for it. Right then, I'll move on to the slippery slope argument. So we've used this argument as to our parents most probably. So if you don't allow me to go to this party, then I will not be a very sociable person, which means I will be depressed, which means I may commit self harm. So this is very fallacious because going to a party cannot guarantee you being a social person. You take an argument A, and then you logically stretch the argument to mean something different, something very different. So next we have the appeal to authority policy. So and its corollary, the appeal to non-authority. So this is actually not very prevalent nowadays, but earlier uh, when uh, Roger Penrose, great mathematician though, but he has some arguments which considered as Prince science. Prince anti Prince science advocates just take that argument and just tell that this has been quoted by Roger Penrose, so it must be true because he is an authority in the area. So which is not. That is why, by definition of science, it does not matter. It does not care if you have a Nobel Prize or a Fields Medal or a Copley Medal or whatever. Uh, it just cares if your experiment is testable, falsifiable, and provable. And also, we have appeal to non-authority, which is quite funny because this is very much more common. So sometimes when we speak about religion, which is a topic in humanities and social studies and all that, so we quote Einstein's beliefs on humanity on religion because he didn't believe in a god and he was probably atheist or agnostic. But if we look at it carefully, Einstein was a physicist and not a what do you call researcher studying religion. So his opinion on religion has absolutely no value because because it is the same as ours because it is not his area on area of study. But Einstein's opinion in physics, yeah, that is a very respectable argument to back up with. Another example of appeal to non-authority is during the pandemic, we take the opinion of a doctor who studies podiatry, which is the study of the foot and its diseases. So, a podiatric doctor's opinion on how a pandemic works is absolutely irrelevant. Although he may have some experience, but he won't have the same experience as a virologist or an immunologist, which is why it can be considered as appeal to non-authority. And finally, we have the appeal to emotion. Appeal to emotion. This is very common back at home when we say that, for example, if you if you are given so if a vegetarian is given meat to eat, he can state his beliefs and politely refuse the meal. But if the host tries to appeal to his emotion, kids in Africa have no food at all. You are lucky to be given food at all. Let's not consider the context really. I know this sounds like a very weird place, but basically don't use emotion to appeal uh, to scientists because as the famous meme personality on TV Ben Shapiro says, facts don't care about your feelings. That's about the time we have actually. I'll be sharing a link with all of you which discusses more logical fallacies in which is very interesting to read. So if you want to widen your knowledge database, just just see the photo here, and you can understand how people try to derail your arguments in logical debates and all that. This photo is something that every person calling himself a scientist must be familiar with. So I hope all of you have learned something about about scientific thinking. Maybe I couldn't cover anything, everything, and all that. So
Thank you, Samarth. It was a very, very wonderful session on scientific thinking. The many wonderful topics were discussed. Thank you once again, Samarth Prabhu. And thank you everyone for attending the KSS. So we hope it was very productive. We hope you absorbed some of the ways of scientific thinking. Hope you apply it or whatever. Thank you for attending.
right, then, thank you everyone. Bye.